Okay, welcome to lecture 14. Today we're going to continue talking about chapter 6 and the remainder of the patterns, and hopefully we'll get into chapter 7 as well. We're past the halfway point in the course now, by the way. In fact, there's 21 scheduled lectures, so that means we're almost at the two-thirds point. It's amazing, eh? There will be 1 week I'll be away later on. That's why we're ahead of the average point. So we talked about a number of patterns the other day. We talked about abstraction occurrence. We talked about, slipping back through them quickly, we talked about the player role pattern, the general hierarchy pattern, the singleton pattern, observer pattern, steadily getting further into the details of design, delegation, very important pattern, focusing on design issues. How do you organize the methods in a class? Okay, so this is not something that you need to think about when you're doing strictly analysis, when you're just drawing class diagrams. Okay, we're going to move on today and talk about a few more patterns. Adapter pattern is the major topic for the beginning of the lecture. We're going to talk about how you can plug some existing hierarchy of classes into turn some lights on here. That's better. Would have looked a bit dark. How we can plug some existing hierarchies of classes into, or existing class into a hierarchy that you're building. Okay, that's basically what we're interested in doing. We want to be able to reuse things. We want to be able to work with work that other people have done effectively. Okay, the problem is that if we're building an inheritance hierarchy, somebody else is already building an inheritance hierarchy, and we want to incorporate some of their stuff, how do we do it? Because you can only have one inheritance hierarchy in the end. You can't sort of say, well, okay, we'll inherit from two things, because we don't want to use multiple inheritance, and you can't use it in Java. Okay, so how do you do that? Well, the adapter pattern is a pattern that helps solve that. Now, adapter pattern can be used not just in that circumstance, but this is one of the most important circumstances for it. Okay? So the idea is to obtain the power of polymorphism when reusing a class, when you have methods that are from somewhere else, that have the functions that you want, but probably not the same signature, in the sense that maybe the method name is different somewhere else in the class that you're reusing. The arguments might be slightly different. Certainly the names maybe a number of things are different. The return types are different, things like that. Okay. So you can't directly use polymorphism. You can't sort of directly import it in either. Okay. The main force here is this force against using multiple inheritance. We said multiple inheritance has lots of problems. It's not available in Java, but it tends to add extra complexity. So here is the overall structure of the pattern on slide 26. Again, we're using the notation where we use the UML stereotypes. On the left-hand side, okay, we have some class that's the root class of the hierarchy that we're building. So we're building an adapter, a class which will be reusing some code from somewhere else. Okay? The superclass of that has a polymorphic method that we want to also have in our adapter. So there's a polymorphic, typically abstract operation, it might be concrete, but there's going to be many other polymorphic implementations of this thing down in this hierarchy somewhere else. I'm only showing one other class in the hierarchy, the actual adapter class. That's the one that we're interested in building that reuses facilities from something else. The reused class is the adaptee, okay? And the adaptee has some kind of method or methods which we're going to reuse. And basically what we're going to do is we're going to have our polymorphic method call the adapted method. So the code up in this little note here says that the result of the polymorphic operation in our adapter, okay, notice dot 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 down to adapter, is return adaptee.adapted method. Okay? That's basically what goes on. Pretty straightforward, pretty simple, right? Can somebody tell me what this method is? What else? What other pattern do we see here? Speak up. I hear somebody muttering it. No, not singleton means there's one instance of a class. Okay, there could be many, many more. Yeah. Yeah, right, exactly. This is a delegation method because all it does is it's calling a neighbor to do some function. Okay, it's got one dot. It's returning something dot something. Okay, so that's a use of delegation in the adaptive patterns. Okay, so here's a real example of adapter. In this case, I'm building a hierarchy of three-dimensional shapes. So we've already seen two-dimensional shapes earlier on in the course. Now here's three-dimensional shapes. So three-dimensional shapes have volume. We can calculate the volume of a shape, given its various dimensions. And the algorithm for calculating volume is going to be different depending on the shape. Okay, so in this hierarchy, the person who's developing it says, well, I want a sphere and I want a torus. A torus is basically a donut with a hole in the middle. Okay? Now, the algorithm for computing the volume of a torus is very, very complicated. It's not a simple thing. Okay, so it would be useful if we could just reuse somebody else's algorithm to do that. And it turns out maybe that we find there is somebody who has produced a torus class sitting on its own somewhere. It could be part of a hierarchy, but maybe it's sitting on its own, just specially programmed. And we say, oh, we'll reuse that code. It does the job. In fact, we might as well reuse the whole thing, the object and all, because it's a very complicated object, a lot of design. No point copying it over. You know, it's somebody else has got control of it. I mean, one possibility is if it was its own class, is we could just work with them to incorporate it and add a superclass and so on. We could do that. But let's say that the names of the methods and so on don't correspond to the methods that we have. We have a volume method. It has calc volume, for example, which is a different name. And it's being used in all kinds of applications. And so we can't just change it to volume and give it a new superclass because it just doesn't quite work. You know, we have to adapt. It's like adapting a European plug to North American electrical system. You've got to have a little unit that changes the shape of the little contacts that go into the plug. Okay, that's basically the concept. Okay, so what we're going to do is we're just going to create a bunch of adapter methods. In this case, it would be return adaptee.calcVolume. And so we store the instance of Tim's torus in our instance of torus. Our torus object is degenerate. It doesn't need to have much of its own stuff. All it has is an instance variable, which is instance variable that contains the real Tim's torus, and then all of its operations, all of its methods are going to just call the appropriate but slightly differently named operations in that instance variable, in that Tim's torus, which is connected by an association. Okay. It's a one-way association, so it's very simple to develop this. It's just an instance variable. That's it. Okay. But nevertheless, it is an association, and it does all the work for us. The object at the end of the association does all the work. This torus here doesn't do much at all. Okay. So that's an example of adapter. Any questions about that? Very simple concept. A lot of these patterns are very simple. The important thing is to understand how to use them, when to use them, and recognize situations when they should be used when you're doing designs. Okay. Facade, another pattern which is also quite simple but also very useful, very powerful when applied in the right circumstance. The concept is that you have a complex system with many packages. Each package might itself be quite complex. And what you want to try and do is you want to try and make a complex package look simpler. So if each package, the public interface to it, the API to it, really has just a few methods in one class, that will look a lot simpler to the outside world or to other packages in the system. And so the system as a whole becomes simpler. Okay? It's complex if a programmer has to manipulate lots of different classes in a package. Okay? So if you have a package with quite a lot of classes, and all of those classes have their own public methods, to learn that package takes a lot of work. And maybe, in fact, you don't need to learn all of the classes in that package. A lot of them maybe could be private. That would be a good objective, because then users of the package don't need to see inside. Also, what is inside becomes more encapsulated and can be the design of the inside of the package can be changed. So lots of objectives we'd like to achieve. The overall problem then is, how do we simplify the view that programmers have of a complex package? The forces, difficulty understanding. We want to make the understanding of a system simpler, and we want to simplify modification. We want to make it. We want to expose less on the API of a package, so that we can change the internals of that package later on more easily. Okay. So as always, the forces are these qualities that we're trying to achieve in our design. So the facade then is a class. Okay, we see the class here which interacts with a bunch of packages. Okay, this notation in UML where you see it overlapping classes like this, overlapping boxes, means that whatever connects to all of them. In other words, we're just talking about an association or associations to a bunch of stuff that we're not getting into detail about. Okay? So a bunch of classes inside the package. Our facade is going to connect to a bunch of these classes, and then the API, instead of being on these packages, will be on the facade, and the facade will delegate to these packages, okay? To these other package classes. And so in the airline system, for example, the airline can be a very good facade class. We already saw the introduction of the airline class. So airline has a number of methods like create regular flight, create new customer, things like that. We can certainly put a lot of methods there, rather than maybe making static methods of person and regular flight. We could have make new regular flight a static method of regular flight, right? Make a new instance of yourself. But the preferable approach is to make an airline. It turns out to be a singleton. Okay. Many facades are singletons, but they don't have to be. It's possible that you have a facade which has many instances. You're still interacting with only one class, but you have many instances of that class to interact with. But in this case, we're also interacting with a singleton. Okay? So find flight, make booking, delete booking, and make regular flight, all kinds of things will be on the API of airline, and then those details of the other classes don't need to be exposed. It might turn out that sometimes you do need to expose some details of some of the other classes, but most of the details, most of the core things can be put in airline. It might even be that you can put all of the stuff in airline. For example, delete booking. We originally put it in the booking class. We said, okay, the user's going to get a booking back, and we're going to that's going to be on the API. We could decide instead to put delete booking here, and the arguments now might be delete booking, and the booking object is an argument to that. Or we could even go one step further, and we could say delete booking and just pass a string, the name of the customer, the booking number, or something like that. And that will go and look up the appropriate booking and go and delete it. So the booking might be totally internalized within the package without ever being exposed to the outside, the whole class. Okay, so there's a number of alternatives. You can have very strong facades that do everything. They require sometimes a very, very strong facade which basically you have to pass all the arguments as strings and things like that, so you never expose any of the other objects, tends to violate object-oriented principles. A weaker facade, where you do as much as you can in the facade, but still have to pass around some of the other objects to the outside world, can be perhaps a good compromise. It's still object-oriented because you're still passing around real objects, but you're doing a lot of the housework kind of stuff, especially a lot of the searches in the facade object. Okay? Any questions about this? Everybody see how, if all I had in my system was a facade and everything else was hidden behind and with private methods and not public, how that might violate object-oriented principles, right? You can, you know, because then what you'd be doing effectively is not the work that other subsystems do wouldn't be calling on object. It would be just, you know, doing very similar kind of work to what traditional programmers would do with passing strings and things like that to all of the operations. But a facade that is a little bit weaker than that, but still does a lot of the work is the objective. Okay, let's move on. The immutable pattern. Now, we have touched on the concept of immutable before. Way back in chapter 2, I briefly mentioned the notion of immutable, and I said that sometimes what you want to do, I think it was in the context of the shape hierarchy, is you want to have objects that do not, that cannot be changed other than the time they're constructed. You construct an object, and subsequently, if you do a computation that would otherwise change the data, what you do is you just create a new object instead. Okay, that's the immutable concept. And so that concept is actually embodied in an official pattern. Okay, like many of these patterns, this is one of the patterns that's been published in books and is quite widely known and widely understood, and I'm showing it here. Although I introduced it in chapter 2, I'm showing it here as a pattern. Okay, so it's an object that the state never changes after creation. That's what we want. The problem is how to actually create such a class. Okay, so we know the concept of immutable. The problem in this pattern is how to implement it so that we can't actually have state that changes after creation. And we want to avoid loopholes. A loophole would be a way which you could get around the immutability and somehow allow changes to be made from outside the class. Okay? Now, in this case, I'm going to show the solution not diagrammatically. I'm just going to show it as text. It's typical to have a diagram in the patterns, but in this case, I'm just showing you a few simple tips written out in English. Okay? So the first rule to ensure immutability is to make sure that the constructor, okay, is the only place where the instance variables are set. Okay, that's pretty clear. But if that's the only place that where you code the instance variables being set, that should be fine. Instance methods must not have side effects. If they did have side effects, okay, that might not be actually setting the instance variables, but it might be changing the value of something that an instance variable contains itself. Okay, what we want is we want to make sure that there's no surreptitious changes. Okay, so the concept there is something like this: that if I have an object, call it A, which contains inside it, and I'm going to use composition to show the containing inside it very strongly, B. Okay. What I would want in immutability is that this B never changes, okay, because it's contained, it's composed as a hard part of A, okay. And so if I say my constructor is the only thing that can set the B as part of A, that's rule 1. Rule 2 is going a bit beyond that and saying, well, I also mustn't change the internals of B either. I mustn't because if I change the attributes of B, in some sense, what I'm doing is I am surreptitiously changing A. Okay, so for example, let's say that this this was some kind of object that represented a place on the map. Okay, let's just say that. Okay, let's say place, and this was a point that says where on the map it's located. Okay. So my constructor says when I create a place on the map, I'm creating it at this place, and I'm not allowed to change it after that. I have to create a new one, so it's immutable. And so I'm creating this point and putting it inside there in the constructor. But the point has got a number of instance variables, x and y typically, right? Maybe altitude as well, it's three-dimensional. And what I also want to be able to do is to make sure that the x and the y and the altitude also don't get changed in B, because that would effectively, surreptitiously allow me to change this. Okay? So instance methods that access properties, i.e. accessing properties of my point class in this case, must also not have side effects. I mustn't be able to surreptitiously change things. Okay? And then a method that would otherwise modify an instance variable has to return a new instance. So in this example, okay, if I had an instance method that said move this town from one place to another, maybe we accidentally put it in the wrong place to start with, then I'd have to create a new one instead of moving it actually. Okay? So that's the concept, and we've seen that concept. Okay? And these are just the rules that you have to apply in order to allow for that concept to be effectively implemented. Any questions? There is a variant on the immutable pattern called the read-only interface pattern. Okay? Read-only interface pattern says, well, okay, we've got immutability in general. But sometimes what you want is you don't want immutability across the board. You want some operations to be able to make changes and others not to. So it to be maybe seen as immutable outside, but inside the package or inside the class, you say, okay, we are going to allow changes to be made. So just inside our package, we can make adjustments to the data that's stored inside the place class. But outside, other packages cannot. Okay? And so what we want to do is we want to set up a structure that will ensure that we have this ability to control where the changes are made. Okay, so the problem is, how do you create a situation where some classes can see a class as read-only, whereas others are able to make modifications? Forces, okay, public, protected, private, blank, those keywords that control access are not, don't give us the fine grain of control we want here, okay? Public says you can call it. Call all the, all these methods. Private says that we can't call them, but what if you want to allow sort of selective calls under certain circumstances? And we'll see those circumstances in the diagram. Okay? The key is, if you make access public, okay, it makes it public for both reading and writing. What you want to do, in some sense, is you want to make it public for reading, but private for writing. So that you can read, you can access the data, it appears to be immutable, but you can't write, you can't change the data. That's what we'd like to be able to do. And so the read-only interface pattern solves this problem. Okay, what we have effectively now is we take our class that we want to have this dual level of access to, and this is, we call this the mutable. This is the mutable class. It's going to be mutable, though. The class as a whole, you can change the instance variables. You can change the values. Okay? Okay? It's got some attributes, which are private, okay, which ensures that, as always, arbitrary operations can't fiddle with them. And it's got some operations, set and get. Okay? These set and get operations will allow you, well, the set operation in particular, will allow you to make changes to this attribute. Okay, so you can have classes that will make changes. So it's mutable. It's not an immutable object. If you want to have some other classes that access this thing as immutable, what you do is you make the mutable implement an interface. And that interface has on it only the get operation, not the set operation. Because this interface only has the get operation, a class which knows only about the interface, all it is able to do is get. Okay? And if you put this read-only interface in a different package, in fact, this read-only interface might have all of the read-only or the get operations for the overall class. If you have an interface that has only those get operations, you put that in a different package and expose that to the world, okay, the world can then do all the gets at once. The world can say get as much as it wants. Okay? And so these unprivileged classes that you don't want to allow to make changes can't make changes anymore. They can only get, because that's all they know exists. Yes, there are real, in the implementing class, there really are set methods. But this class doesn't know about them. Okay? And so the concept is that you've restricted control by not allowing the other classes to know about the existence of certain methods. What is the loophole here? What could there be if proper care isn't taken? What is the potential loophole? Think tricks you could do in Java, yeah. Okay, I think I heard what you said. There's nothing physical. Can you say this again a bit louder?
Nothing really that stops an unprivileged class from implementing mutable as opposed to interface.
Well, unprivileged class isn't implementing anything. Unprivileged class is just calling stuff that it knows about.
Sorry, not implementing, but I mean using mutable as opposed to interface.
Okay, he says there's nothing stopping unprivileged class from declaring variables of type mutable instead of type read-only interface. If I declare a variable of type mutable, okay, then yes, I have access to that. I have to import this package to do that, because this would be in a separate package. But I could do that. Another thing I could do too, which would be almost equivalent to the same thing, is I could cast the read-only interface to mutable whenever I felt like doing that. Right? So if I have one of these things, I have a variable of this type, and I just cast it before I make the call, I can access any of the public things down here as well. Okay? So this pattern gives you some control. It doesn't give you total control because there are loopholes. But it tends to reduce opportunities for bugs. Because you're basically saying, here are the methods that we want you to use in this outside world. Okay? Please don't use other stuff. If you use other stuff, you're deliberately violating some boundaries here. And there's a reason for those boundaries, Otherwise, you wouldn't have done this. I mean, it takes extra work to create this interface, which has a subset of stuff. So, what's the point of deliberately violating that? That this is here for a reason, to stop you accidentally tripping over yourself. And programmers don't, as a rule, set out to trip over themselves and start bypassing restrictions. The restrictions are there for a reason. Okay, it's part of the design. Okay, so most of the accidental changing of mutables, which wasn't the design originally didn't intend, is done because a programmer sees, oh, we do have a set operation, great, I'll call it, without realizing that it could cause some inappropriate effects. Okay, and so by creating a read-only interface that has a subset, this allows us to tell the other users, use this. It's a safer class to use in the outside world. You can do all the getting you want. Let this other package worry about the setting. Okay? Any questions? Okay? So I could have a mutable person class, which has some operations and attributes, first name, last name, and a set first name, set last name, get name. This mutable person class might be stored inside a subsystem that has to do with changing the vital statistics information about people and updating personal information. And there's a package that deals with that. However, because person is a class that tends to be used all over the place in many systems, you say, well, okay, outside of the confines of the class that is allowed to fiddle with things, all we're going to have is a single interface that can be declared as the type of variables, and objects typed with this interface can be passed around, and there's only the getName method there in that. Okay, I can get the person's name. That's all I can do about them. The rest of the information is private. Maybe even things like social insurance number can't be accessed when they're not needed. You know, that adds a level of control. Here's the information that we want to expose. Everybody has student lists, you know, have to have names. But the system that's doing the scheduling of exams, that's looking at people's names and printing out who's seating where, doesn't need to know anything else about the people. Okay? And so just to make sure that programmers don't accidentally start accessing that information, we'll just pass around the interface person. Okay? And to all intents and purposes, everybody looking at this thinks it's a class. Okay? You know that you have something which looks like a class, acts like a class, behaves like a class, has instances, because the instances are instances of its implementing classes. You just declare variables of type person, and it acts very much like a class. Your past values, you can't say new person. That's the only thing you can't do. Okay, the creation has to be done of the actual mutable person. But once you're past objects of type person, you don't even need to know this is an interface, basically. From that point on, you just treat it as if it was a class with its operations. Okay. Anti-patterns then. One anti-pattern is to make the read-only class a subclass of the mutable class, and to override the methods that modify properties so that they throw an exception. This is a trick that people have used to achieve similar effect. So I flip these around. My immutable, my person, is a subclass of the mutable. And this has got things like set first name, set last name, throw exceptions. But that has some, that actually is totally a different design, because effectively under those circumstances, I don't have a read-only interface with a mutable case. I have a version of the class which is truly immutable. Okay? If I have a subclass of mutable which overrides set first name and set last name to throw exceptions, any instance of that subclass I will not be able to call ever set first name and set last name, because they will always throw exceptions. I'll only be able to change the values in the constructors like a real immutable. Okay? So it doesn't give me this dual level of control. It only gives me one level of control if I make that a subclass. And secondly, it's bad practice anyway to override operations and have the overriding versions throw exceptions. Occasionally that's acceptable, but as a general rule, a better design is to try and avoid that. And this design we have here on slide 33 does avoid that. Okay? So don't do it this way if you have the other option, is the rule. Questions? Now you might be somewhat pleased to note that we're getting close to the end of the list of patterns. One of the things is that there are thousands of patterns out there now in the world to study. All I'm showing you here is a catalog of a relatively small number of patterns, because it's too much to expect you to memorize a large number of patterns. My suggestion to you is that what you need to do is, as you're practicing over the years, that every now and then you go back and look at catalogs of patterns and learn a few new patterns. A lot of the patterns will be things you say, you know, I've been doing that, or I've been thinking about doing things that way. Now I know that it's a pattern that everybody kind of recommends as best practice, and all of a sudden it clicks and you get it. And then later on, when you're doing design, you think you can do your design faster because you recognize patterns. You say, ah, yes, that's a proxy, or that's a read-only interface. And you immediately think about the pattern. So as you gain experience in industry, read more about patterns, and that'll accelerate your learning process and accelerate your ability to be a good designer. But you need to start somewhere. So we're starting you off with a selection of patterns that are broadly useful. I'm not covering all of the Gang of Four book here. I'm covering a few of my own ones. I'm just covering a selection of patterns that tend to be particularly useful and interesting. Okay, and it's up to you then to go on and as part of continuing education to expand your knowledge of patterns in industry. And you'll learn more as you through other years of this university degree program too. Proxy pattern. Okay, what's the context? Time-consuming and complicated to create instances. Okay, some instances are big and bulky. An instance of an image, for example. An instance that represents an entire file. Any instance that's got a lot of data in it, a lot of detailed data. Okay, big, complex, bulky instance. Okay, sometimes it's time-consuming to create that. So if, for example, I have a client-server system, and I have one of these instances existing on my server, and I need all of a sudden to use it in my client, it's going to be a lot of work to drag that up from the server as a bunch of messages or one big complicated message, and then construct the object on the client side so I can use it. Okay, a lot of work to do that. Same thing if I've got a big complicated object on a database. Instead of reading it off the database and building it as an in-memory object, it take a lot of work. And so sometimes I say to myself, well, you know, there's too much time delay, too much complex mechanism, and sometimes I don't need to do very much. Sometimes all I need to do with an image object, for example, is to say, how big is this image? Right? I don't always need to print out the image, display the image, so why drag this whole image over the network, let's say, and build it in memory when all I need to know is how big are you? It would be nice if there was a way that I could have some other little object that could sort of stand in place of the big object that allowed me to do some simple queries like how big are you to an image, but without actually having to get the entire image. And these small little objects are the things that are called proxies. The problem is, how do we reduce the need to create instances of heavyweight objects? Okay, the forces. Number one force, we want all of the objects, or we want all of the capabilities to be available to us. We want to be able to work with images, and we want to be able to work with other big bulky objects. Okay, so we want to be able to work with them, but we still have this problem of reducing the need. We want to improve efficiency, reducing the need to do downloading and things like that. Another force is we want objects to persist from run to run of the same program. This is a related kind of a force that we'll talk about. One possibility is that while you say, well, okay, rather than taking heavyweight objects, moving them from one place to another, we could just use everything in memory. You know, everything exists in memory in our own local program, and therefore there's no need to ever get an object from one place, put it somewhere else, because it always exists in one place. But in reality, things don't work that way. In reality, you do have servers and clients, and you want to save things on a server. You do have databases, and you want to save things on databases. So there will be a need to drag stuff from these places where you save them, servers or databases, and bring them into your memory. There will be a need to do that. And there will be a need to save them back there as well. But it would be useful if we could sometimes avoid the necessity of having to unnecessarily move these bulky objects around. So, the solution then looks something like this. Okay? First of all, we have a client class. This is any user of these objects. Any user of these objects. Okay? I'm showing a many-to-many relationship. Client accessing many proxies, proxy accessed by many clients. Okay? Could be less than many-to-many, but many-to-many is certainly one possibility. Access is typically in the proxy context, one-directional. So my client grabs a hold of an image or grabs a hold of some other big, bulky structure. That big, bulky structure contains information that doesn't know about who's grabbed hold of it. So the image doesn't have details inside about who's displaying the image. It's just a standalone complex structure. That's the normal, typical pattern. It doesn't have to be. Occasionally you could have two-directional access here, but the normal structure is a one-directional access. By default, clients access things called proxy objects, little, teeny, small objects. Okay? These small objects then can, and this really I guess should be 0 to 1 here on the connection to heavyweight, can contain the heavyweight but don't have to. The heavyweight object, let's say, is the real image, the real big fat object. So when the client wants to work with this, well, let's imagine the client doesn't really care. All the client knows is that the client can access the image, okay? But what the client is given is the proxy. And the client can send some methods to the proxy. How big are you? Well, maybe the proxy has that information built into it. Are you a black and white image or not? Well, maybe the proxy knows that. Those simple questions can be answered without having to actually load the entire heavyweight object. Okay. But if then the client says, display yourself on this screen, at that point, the client has to access the full heavyweight object and effectively delegates any of these methods to the heavyweight object. And under those circumstances, this object has to be loaded into memory. And the client might have mechanism to actually load it into memory and then actually pass on, delegate on requests to the heavyweight. Generally speaking, both the proxy and the heavyweight are going to implement a common interface. So they have the same operations. They have, in the case of an image, get dimensions, get color map, get things like that, and display. They both have a display. But the proxy's display delegates to the heavyweight's display. Okay. So they're going to have the same methods. They look the same to users. The users don't really care, except that the client, will access a lightweight proxy version because, by default, to avoid the overhead of loading when we don't really need to load. Okay? This is a pattern which is used deep inside detailed design. You don't do this kind of pattern when you're doing domain analysis. You do this kind of pattern when you're thinking about the innards of design, when you're working on hooking up databases to your system. It's very common with working with databases when you're dealing with client-server architectures, things like that. Okay, when you're doing domain analysis and you're representing the world, all you're concerned about then are that there is some kind of client accessing some kind of object, maybe image, and you don't care that you have all this heavyweight proxy class interface kind of structure around it. Effectively, what's one domain class, like called image, turns out to end up being an interface in two classes at design time because we decided that we're going to split it into a heavyweight and a proxy version. Okay, so here are a couple of examples of this triad. Okay, the top one is for list. Okay, so I have a list. I'm calling it list IF, list interface. There's a tendency for people to suggest that if you have an interface, you call it IF so people know it's an interface because they act so much like classes once you declare variables of them that people don't always know. It could be useful to call it IF. Two implementing classes, list proxy, persistent list. The list proxy is the small version. The persistent list could be a massive structure that has 10,000 items in it. But if all you ever want to ask is how big is it, the proxy can tell you the size. So you don't have to load the list into memory or load it from the server to the client. You just have a proxy representing the list, and that proxy can do certain things. It can ask, it can go and ask the persistent list, how big are you? And then return that value. But if the user really wants to start iterating over the list, it's going to have to load the list into memory, potentially. Or alternatively, maybe even the proxy decides not to even do that. Maybe the proxy creates an iterator, and that iterator is going to, as it iterates through, load each element one by one into memory. So it actually never loads the entire list. That could be an alternative implementation. The point is that the proxy is smart. The proxy only accesses and loads bits into memory when it really, really needs to. But from the perspective of the user of the proxy, the code that's using it thinks that the real thing is there, and that's what really matters. Okay, the persistent list could be, in fact, a table in a relational database. Okay, and so this list, when we declare a list, is a list of elements in this database. And what's going to happen in the proxy is it's going to be going and doing queries one by one to get elements out of this database table. But from the perspective of the user of the Java program in memory, there appears to be a list. It appears to be in memory, but it's not really. Okay, it's really going off and accessing the thing that's off somewhere else in some totally different computer, somewhere else on the internet maybe. Okay, so that's the power. The proxy represents some more complex structure somewhere else. Another example, I could declare an interface called student. And all of my classes that work with students could directly connect to that student. They don't even need to know there's a list proxy. On the previous diagram, I showed the client connecting to the proxy, but the client can also connect to the interface itself. Okay. So in this case, I'm not even letting on to my users, really, that this is an interface. But it turns out that there is a student proxy and a persistent student underneath it. They both implement the same interface, and so whether I've got the proxy or whether I've got the real student, my programs don't really care. My programs can still do all their work, because if they happen to have a proxy, the proxy will delegate to the persistent one when needed. Okay? And so if I'm working in a client side, I might have proxies. If I'm working on the server side, I might have access to the real persistent student objects. But from the perspective of using the thing, if I just use the interface, I don't care, I don't need to know. And that not needing to know is a very good thing in software engineering, because it saves us from worrying about the complexity that's going on underneath. Proxy is a very important pattern in software architecture. When you go on and take more advanced courses in software engineering, and you'll learn about persistence and distributed objects and things like that. Some of you will. Those in the software engineering program will get into this kind of stuff in a lot of detail. Proxy will be one of the dominant patterns that will show up in a lot of this stuff. Okay. Any questions? Again, going out of this lecture, you should get the core concept. The core concept is representation of a complex object by a simple object. That's really all there is to it. The fact that we've got an interface that is sitting above both of them is a nice additional nicety. But the real core thing is that simple object representing complex one. And that is the last of the patterns that we will look at. Okay? The remainder of this lecture, I want to just show you an implementation that is taking advantage of some patterns. I'm going to briefly go over this because it's useful, interesting to think about. But I'm going to primarily leave it up to you to go and think about it and study this design in more detail yourself to try and understand how it works. Okay, I'm going to overview now. This is an extension of OCSF, an extension of the Object Client Server Framework. So we know that in the original OCSF we had abstract client, abstract server, connection to client, the three classes shown at the top of slide 38. That's all it was, right? We've extended OCSF to add a bunch more mechanism. And this actually makes OCSF appear to be quite a bit more complex than it really is. We'll see later on how this can add some power. Okay, let's take a look at the client side first of all. Okay. Client side, we subclass abstract client. Remember we said that the normal way to use OCSF is to subclass the abstract client to create a class which is your application class, concrete version of abstract client. In this case, this framework extension is doing that for you. So we get adaptable client as a concrete client object that's got implementations of certain operations. So it's got connection established. Remember, this is one of those methods, those hook methods that you can implement, do something. It's got connection closed, another one of those. And it's got the all-important slot method, handle message from server. Okay, remember we said this is the only thing you actually have to implement. The other ones you could ignore if you want. They do nothing, you can leave them do nothing. But adaptable client will in fact implement all of them. But it has to implement handle message from server. So it has a default implementation of that. Okay. And then what we have is we have this notion of observable connected up to this thing. Okay? We have a little observable hierarchy. And let's just worry about what's on the left-hand side. Observable is built into Java. Right? Observable client is a subclass of observable. We have to. Observable is always, any observable class is always a subclass of observable. So we have observable, and we have observable client, a subclass. Observable client is also going to implement a lot of the stuff and is going to delegate a lot of stuff to it's going to delegate some of the stuff to adaptable client. Okay? And basically what's happening is what we want to do is we want to create a version of the OCSF classes, in this case the client class, that is observable. Remember we said we've got this observer pattern? Once I have an observable client that effectively acts like an adapter, okay, is using the facilities of my main client mechanism, then then what I can do is I can create observers. Okay? I can create observers, which could be anywhere, and these observers have a very weak connection to observables. Go look back at the observer pattern, and you'll see that the observers implement this interface called observer. And so any class anywhere in my system can implement this observer interface and say, I want to observe the client. And effectively what I'm doing is I'm observing handle message from server. But I'm using the observer, the weak association to do that. So any piece of my system can act as an observer on messages coming in from the server. And basically what happens is that we have delegation from the adaptable client to the observable client. And then the observable client, when it gets any messages coming from the server, it's going to call its send to all observers, and they will in turn call the update method of my observers. Okay. I just said a hell of a lot. We're integrating several patterns here. We're integrating the observer pattern, we're integrating the adapter pattern, and we're doing delegation. Okay? What I'm going to do is I'm going to leave it up to you to take it from there and go and figure out how those patterns are being integrated. This is the purpose of having this here to some extent is an exercise to force you to think about how these patterns are being integrated in this one extended framework. The server side works the same way. Server side, we have an adaptable server that is a concrete implementation, and we have an observable object. These two objects that work together using the adapter pattern. Remember, with the adapter pattern, you always have this one-to-one association. You have an adapter and an adaptee, and they delegate to each other. typically one way, but they can delegate back the other way. The adapter can become the adaptee and vice versa. And that's actually, there's a little bit of that going on here if you look at it closely. But basically they work closely together because, and the reason why we need adapter, can anybody tell me why we need an adapter in this circumstance here? I don't expect anybody to get it yet, but if somebody does, it shows that you've really got what we talked about this morning about adapters. Can anybody get why we need to use the adapter pattern here? I think this will be a video that several of you will go back and look at twice. Can anybody, remember we said, we had this Tim's torus example. We said we've got an implemented object, Tim's torus, right? And we're creating our own new hierarchy. Okay? The purpose behind adapter, one of the key purposes is you want to be able to reuse an object that is already part of a hierarchy. And therefore you can't just build it in directly. So what we have here is we already have an abstract server. We already have a hierarchy of servers. We already have a hierarchy of observable. Observable is built into Java. So we can't just make observable server and adaptable server the same thing. We can't just make adaptable client and observable client the same thing, because if we made this just one class, which would be a cleaner design if we could do it, then we would have to subclass observable. And we've already got a subclass. The adaptable client already has a subclass. Is already a subclass. And so because we have two separate hierarchies, two separate superclasses, we have to make two separate subclasses and connect them together using the adapter mechanism. Think about European 240 volts as the abstract client. North American 112 volts, 120 volts as the observable. Okay? Well, those two things don't work together. We've got to create one subclass of each and connect them together using an adapter mechanism. That's what's going on here, really. Okay? I see some blank stares. How many people think they have at least a vague idea of this? Okay, that's good. That's comforting. All right. How many people have no clue? That's also comforting. Nobody has no clue. Good. So at least you have somewhat of a clue and you're beginning to get there. All right, let's move on. Big fat diagram here. All I'm showing in this diagram is that I'm implementing a whole bunch of stuff. Okay, in my observable client. Okay, so I have a whole bunch of stuff in my adaptable client. I have a whole bunch of stuff in my observable client, and these observable things, they're going to use my notify all observers which will notify update, but ultimately the observers will get back instances of the observable object and they can ask these questions. So I got tons and tons of all these things are doing are delegating. Okay, they're just delegating to the adaptable client. Okay. As I said, we have to adapt, so that's why we're doing this delegation. I'll let you look at that yourself, but the key to use this observable layer is to create a class that implements the observable interface. Sorry, the observer interface. Okay, these are the classes, one or more classes in the core part of our code. It's going to be registered as an observer. Okay, so in the standard way that you would register anything as an observer, and it's going to have an update method. Any observer will have an update method, and its update method, when it's called, it will be passed the observable. In this case, it will be the observable client or the observable server, and possibly some other message, which could be just a nil value. The point is that when it gets this message update, it knows that some change has taken place, and at that point in time, it can react and find out what that change is. Typically, the message would say what the change is. It would say message from server or something like that. It might in fact be the message from the server. That would be a normal way of doing things. Okay, we'll wrap up chapter 6 then by just going over a few risks. All things we do have risks. So the risks in patterns is to think that patterns are a panacea. Patterns solve all of your design problems. Okay? Or worse, that anytime you see a circumstance where a pattern might fit, you apply the pattern. Okay? You always have to assess, is this the best solution? So even though a pattern might apply, it might not be the best solution for this problem. Maybe some other solution might be better, because there might be other forces that might be stronger and another pattern or another design might apply. Okay? So patterns are guidelines. They suggest that under certain circumstances, this way of doing things is good. But there might be overriding circumstances. So you need to understand the pattern in more depth to really choose whether to use it or not. Second risk is people get the idea behind patterns and they start writing their own patterns. Okay? You should only write patterns yourself once you become an expert designer. Okay? Patterns are wisdom of the experts passed down to people who are learning and to the masses of the design community. Okay, so don't set out to write patterns until you're an expert, until you really have a sense of what's good design and what's not good design. You've been doing it for several years, and you can say, okay, here is some wisdom that I have been using over and over again, and furthermore, I've seen other people using the same kind of wisdom, so I know it's generally accepted in the design community. It hasn't been documented as a pattern, but it should be, and therefore I am writing this pattern in order to publish what is considered best practice. Good design practice, okay? So don't just write patterns off the top of your head. Wait until you're an expert and you can say this is really to be used by everybody in the community. It's quite common, in fact it's done here at the University of Ottawa, that graduate courses are offered in pattern writing. So once you get to be a graduate student, you've had several years of experience in industry hopefully as well, that you can take courses in patterns and learn quite a bit about them. That brings us to the end of chapter 6. Any questions? Hopefully you have a sense of what patterns are at least. And we will now move on then to chapter 7. In chapter 7 we're going to talk about users and their tasks. The human element of software engineering. The human element of software engineering is often downplayed. People often get really heavily into the technology. How does this stuff work? We've been talking about technology a lot. Chapter 5, chapter 6 were all about technology. Class designs, pieces of architecture, patterns, things like that. Programming. All of these issues are things which a lot of people go into software engineering because they feel they like working with cool technology. But a software engineer must work a lot with humans. We talked about that to some extent in chapter 4 when we talked about requirements. Now we're going to talk about aspects of users and their tasks that are more design-oriented. We're going to put this all under the overall title, a lot of this under the overall title of user-centered design. User-centered design is doing design where you're always thinking about the end user. You're always thinking, what is going to be best for the end user? Now you can do technology-centered design, which is saying, what is all the cool technology we can put out there? But unless you think about the end user, you're often going to end up with disasters. A lot of the current tech slumps, disasters, have been caused by not adequately thinking about the end users. Okay, a lot of the current slump is caused by technology companies, so the Nortels, JDS just laid off another 1,000 people today. The whole chain of effects comes about because end users of the technology, end users being people who use phones, people who use the internet to browse and use the web, ultimately they're the end users, right? People didn't think about them enough. People became too exuberant, thinking that, wow, everybody's going to be using vast amounts of internet power and all kinds of fabulous new phone features and all kinds of new wireless capabilities much faster than in actual fact. ended up being the case. I mean, that's not the only cause of the tech slump, but it's certainly one of the underlying causes of it. And so all these companies started building all kinds of technology-centered design. And a lot of it was good technology, still will be, hopefully, once we get out of the slump, and will end up being used by users to some extent, but some of it won't be. Some of it's overpriced, some of it doesn't actually fit with the real needs of the users, and some of it might fit with the real needs of the users in the future, but you have to think not only of the real needs of the users, but also what their attitudes are, and how much money they have to spend, and what their experience is, and all kinds of issues. And unless you understand all of those kinds of things, you're not going to be able to come up with products that are viable and will actually sell well in the market and make a profit for your company. So user-centered design says, think from the user and think back from the user. We'll get to the technology from thinking what the users need, how they behave, what they want, how they're going to use it, what difficulties they're going to have. Take a step back from that. What technology do we need to solve their problems? And then maybe second-level technology is technology that supports first-level technology. But if we work back from users, we'll end up being much better off than if we start with cool technology and hope that users will end up using it. And this doesn't work. We've seen that. Okay? So the core thesis of user-centered design is software development should focus on users. We need to understand them as people. I recommend that software engineers take a course in basic cognitive science or psychology. Okay? However, not all psychology courses are equal. You don't need to learn about Freud. You need to learn about how people think when they're doing ordinary everyday tasks, right? You know, as opposed to, you know, the different mental instabilities they might have. That's less relevant. Okay? Once you understand your users, you design software based on this understanding. You ensure users are involved. So you bring users in to test out early prototypes frequently and over again. And you pay attention to the nuances. You see, are they enthusiastic? Are they not enthusiastic? What difficulties do they have? What do they find easy? And you change the technology to fit the users so that it will end up being used effectively. You design your interface using guidelines for good usability that have been developed over the years by lots and lots of people studying software in the hands of users. There's a big area of science called human-computer interaction that involves studying how people work with computers. There's a broader area of ergonomics that involves studying how people work with any engineering artifact. Okay. And a lot of this is done using good scientific methods, just like physics and chemistry. Okay. Very good studies that have proved that certain techniques work better than others. That people see certain colors better than others, and so you should use certain color combinations, or certain font designs are better than others, things like that. And finally, as part of user-centered design, have users work and give their feedback about all issues, including online help, including user manuals, and so on. There is a course in the software engineering program, SEG 3120, that I sometimes teach. I probably won't be teaching it the next year or so, but I probably will teach it again eventually, which focuses on user interface design and user-centered design. It's also an elective program in the computer engineering program. Highly recommended. Okay, focusing on users can benefit us in a number of ways. Reduce training and support costs. Okay, a lot of the cost that ends up sunk in software companies is the cost of supporting users, running help desks. For custom software, a lot of the cost is in training, and a lot of companies that buy software have to put a lot of money into training as well. If we focused on the users to start with, some of this cost can be reduced. A lot of it can even be eliminated totally. Another cost reduction, reduce time to learn the system. People have to spend a lot of time learning software when they first get it. Even experts. I just spent the last day learning how to use a new version of the Macintosh operating system. Okay, I consider myself pretty expert in computers, but I still had to spend a decent amount of time. Luckily, it's reasonably usable. I didn't have to, a lot of it was intuitive, which is good, but I still had to learn some. The thing is that you want to make sure that it's only one day instead of, a week, because that's a lot of money. Greater efficiency of use, so not just learning time, but if you do user-centered design, the software will be faster to use on a daily basis. People don't have to spend time fiddling with the software to get it to do what they want. They can just click a button and it does what they want. Okay? So user-centered design will get it to that point where people can quickly do their work with it, rather than slowly. One of the big things we have to worry about there is response time. Vast amounts of time, probably billions of dollars are wasted a year with people sitting, waiting a few seconds for the system to come back. Add all those seconds up, it costs billions. If we could cut that down by half, to 1 second instead of 2, or better yet, to 1/10 of a second, we can save a lot of time. People can be much more productive and save that money. Efficiency of use. And that comes out of focusing on users, discovering what they do, how much time they have to wait for things, and add it all up, figure out the cost savings. A lot of this pays off big time. This is one of the biggest areas where you can have a financial impact on your company, is to improve usability. Reduce cost by only developing features that are needed. A lot of software is shelfware because it's not used or contains features that are not used, which were developed at great expense. Okay? And if you work with the users from day one, find out what they actually were interested in and worked on those things first or only, then you're going to save a lot of development work that's never going to be used. Reduce costs associated with changing. Okay, another huge area of expense is changing software that once it's put into practice is discovered not to be very usable and you have to maintain it. I mentioned much earlier in the course that if you try to change the design, it's much more expensive than getting it right the first time. So getting it right the first time by understanding users saves you vast amounts of money. Prioritizing of work. Iterative development is the style we want to follow. We want to say, okay, we're going to develop the first release, the second release, the third release. But if the third release is the release that contains the stuff the users really want, then you're delaying getting the software into the hands of the user. So if you prioritized and put the important stuff in the first release, because you work with the users and find out what they are going to use right away, then you get the software into the hands of the users faster. So prioritizing is another way. And finally, greater attractiveness, important for off-the-shelf shrink-wrap software. You make the software more usable, it will sell more because it looks better, people get a better feel for it, it gets better reviews in the trade press, and people will be attracted to buy it. Some of that is cosmetic, but some of that is just first time people try to use it in a demo version, they say, oh, this is awful, I'm not going to use this. Okay, so look at all these points. All of these points are different points that independently can save you huge amounts of money. If you can do user-centered design, you can impact all of these things and dramatically cut costs. And this is a point that's very rarely really understood in software companies or companies that produce software. So user-centered design is a very, very important area of an overlooked area of software engineering. We often have a handle on the technology side. We often do have people who are very technically competent at doing design from a technology perspective, but much weaker at doing it from a user perspective. Any questions about that? Okay, so we say we don't want to understand our users. How do we do that? First thing, understand their characteristics. What are the goals for using the system? So what are the goals of students? Understand students. Students want to graduate fast. They want to make sure they take courses that can help them get jobs. They want to keep their options open. They want to have courses that are fun. They want to have courses that have professors they like. They want to have courses that they're going to get good grades in. Tons and tons of stuff, okay, that students really want. It's not just blindly registering in whatever course happens to be there or next on the list, right? So if you understand students, you can develop a better registration system. If you understand shoppers, what difficulties do shoppers have? You can make a better e-commerce system that tracks them to things that they're more interested in. If you look at the best e-commerce sites, you'll see they're constantly adapting and adding features that help you to pick things. Oh, they help them sell more stuff. But by helping you pick things that might be attractive to you, that helps them sell more stuff. Okay? What are their patterns of use? Are they frequent users, infrequent users? Do they do a lot of stuff at once and then forget about it and have to come back and learn the system later on? Demographics. What's their age groups? What are their skills in their backgrounds? Where do they live? All kinds of issues that can bear on issues to do with the system. If you develop a system today and you develop it purely for high-speed internet, okay, a lot of people are doing that. A lot of websites only work on high speed because they're tremendously expensive in terms of the images they drag down. But guess what's the biggest sector of growth? The biggest sector of growth worldwide is not high-speed internet, it's 56K modem internet. Because countries all around the world are coming online fast. And they're coming online at 56K because all they got is old dirty phone lines, or less than 56K in fact, probably much less than 56K because of the dirtiness of a lot of phone lines. They don't have high-speed access, they won't have it for 20 years or more. Okay? So the big growth in the internet, if you're selling worldwide or you want information to be made available worldwide, is slow speed, and therefore you have to make your systems work slow speed unless you want to limit yourself to a much smaller market. Okay? Interesting thought, because probably 90% of you have high speed. But you have to be aware of the demographics of the wider community. How much do people know about computers and the domain? Unless you have a handle on this, you're not going to be able to, you're going to be maybe expect too much of them. You're going to have terminology in the user interface they don't understand. Or, alternatively, you're going to patronize them. You're going to develop software that, oh, gee, I know this. You don't have to tell me this all the time, over and over again. You know, you got little Microsoft Bobs popping up and giving you way too many hints, you know, when you're an expert. You want to avoid that among people who are experts. Physical ability, another thing. Are people actually able to use the mouse or use the keyboard? There's lots of disabled people. In fact, there are laws on the books in many countries that require you to, for example, make your system work for blind people. So you can't rely just on images. You have to have backup text and things like that. And finally, psychological traits and emotional feelings become important. People get frustrated with computers. People have likes and dislikes. Understanding those is important too. Okay? So we'll leave it there today. Next day we'll pick up and talk about use case models. Good luck on the test tomorrow.